Hello, everybody, and welcome for another episode of American Profiles in American Funded Research. I'm excited today because I have a new guest, Dr. Anatoli Polkovnikov, and he studied initially. He got a master's at St. Petersburg State Polytechnical University, got his PhD at Yale University, now works at Boston University, and he's had a couple of awards. He was a Sloan Research Fellow, and he was part of the Young Investigator Program for the Air Force research arm. So, did I get everything correct there?
Uh, yes, everything's great.
Awesome. So I had you on today because I wanted to discuss the project, specifically and I do want to actually, before I start that, I do actually want to have a discussion with you also broadly about research, because you had in an earlier email with me,
Mhm.
you had some very interesting points that I would love to highlight, but I'll save that for later. But I wanted to talk to you about your project, the non-equilibrium dynamics in closed interacting quantum systems. So I just wanted to start off letting you have, give us a brief overview of the project, and then maybe we can dig into the details a little more.
Yes, sure. Just want to say that this project, I'm lucky to be funded by NSF for quite a few years. So when I joined Boston University in 2005, I think I got this award in 2006, and it's basically a continuing grant. So my topics evolved a bit through these years. Yeah, mostly like if I want to like describe in general world, or one of these very complicated problems we are facing, not just in physics, in chemistry, biology, other disciplines. So of course I know I can say with confidence only about physics. And the problem of people call it the problem of emergence. And one of the great physicists of like last and beginning of this century, Phil Anderson, formulated very nicely. More is different. And basically, the main issue is that we are dealing with chaotic systems. So we kind of can know that when we just take very first course in physics, when we study, say, a pendulum, we know that we can write a simple equation, like it's mathematical equations, like set of rules, and we can predict what this pendulum is doing. Then, of course, theory evolved, and then later we learned that our little pendulums, like atoms, they actually satisfy quantum equations. But the idea is still similar. We solve a slightly different equation, and we can more or less predict what happens to a given electron in, say, hydrogen atom. But once we add two electrons, so you might think about like classical analog, we can easily explain motion of moon around the Earth. But once we add a second moon, another planet, or we can think about Jupiter or other planets, the motion becomes chaotic. Chaotic means that it's super sensitive to like small perturbations. And we, of course, know chaos from weather patterns when we cannot really predict much. But at the same time, chaos also leads to what's known as statistical mechanics. Like if we look into sun, we know it's yellow, even though we have no idea why what each atom is doing. Like there are many nuclear reactions and so on. And we can still predict with great accuracy what's the spectrum from the sun, because chaos leads to so-called like statistical mechanics, which is governed by laws of large numbers. And of course, it applies not only to physics, but many other systems. And then we can make some predictions combining sort of microscopic theory, these rules, and laws of statistical mechanics. And this is basically sort of the main challenge is to find the right combination. Things, of course, become very difficult when sort of when we are away from equilibrium. So, and this is kind of a subject of main subject of my work, because if you sort of drive the system, like you can imagine again some turbulence or tornado, this is a air which is not in equilibrium, and yet it's chaotic. And their description is most challenging. And broadly speaking, if you think about my research is kind of splits into two main categories: how we control the chaos and how we understand the chaos. So controlling the chaos means like which kind of processes we can design to make sure that the system is non-chaotic. And for quantum systems, non-chaotic means, for example, we can do quantum computation, because chaos means that instead of getting the desired answer, we get some turbulence in our code, and it predicts something totally different. And of course, computation is non-equilibrium process. We can think about state preparation. So if we are in the lab, we want to prepare some non-trivial state of matter. And the question how we can do it such that the system doesn't enter this chaotic regime. But of course, to answer these questions, we need to understand what chaos is. And especially in quantum systems, it was very challenging because we don't have like trajectories, microscopic trajectories. We have uncertainty. We have particles and waves at the same time. But nevertheless, there were like many recent developments, I would say, including done in my group, and we are sort of following this. And of course, there are some other questions, like how we understand difference between classical and quantum. And we know that, again, if we take our example of tornadoes, collisions between molecules are quantum. You cannot describe them correctly without quantum mechanics. But of course, large classical patterns are classical. So while in this case, it's more or less intuitively clear where the borderline is, in many situations, it's very difficult to say where quantum ends and classical begins and how we accurately describe those, how we match them. And this is sort of, and chaos also plays a big role there. And this is sort of another part of my research.
Thank you very much for the introduction. So, being a having been a physics major myself, um, what I have a question about the chaos because um, when I think of chaos, I think of purely deterministic, right? Like if you knew the exact initial conditions of the say the three body problem, you knew the exact initial conditions, you could still map out in time all the way into the future what's happening to the system. It's deterministic in that sense. Um, Obviously, we don't have access to the exact initial conditions, which is why chaos is such a problem. But from a quantum standpoint, I always think, for me, quantum I always think is as something that's non-deterministic. So how do you bridge that gap?
Yeah, it's an interesting, very interesting topic. But let me maybe start from like one question I always ask students when I teach quantum mechanics. I taught it for many years, quantum mechanics. And it's actually is along the lines of what you are saying. So I always ask them when we start, I talk about graduate students who already took some quantum mechanics, so they're already familiar with Schrodinger equation and so on. I'm always saying, which systems are more deterministic, classical or quantum? And there is a standard answer which all of them give, classical, for exactly the reasons you are saying, that we know exact positions, momentum, and so on. And I'm saying, okay, let's just take a square well or harmonic oscillator, and let's consider stationary states, quantum states. Which states are more classical? Low energy states or high energy states, like low temperature, high temperature? Of course, they all say high temperature because that's how we get Boltzmann gas. At high temperatures, it's classical. At low temperatures, it's quantum. We get some, I don't know, some Fermi liquids or superfluids, superconductors, and so on. Okay, and then I'm saying, but where do we have larger uncertainty? At large energies or small energies? They score, of course, at large energies. So then I repeat the question, which systems are more deterministic, quantum and classical? And after that, I get complete silence because you come to a logical contradiction. So I would say that a lot of our thinking is kind of biased towards big classical objects. But one has to understand that if we deal with sort of small systems, as we make them more classical, they become more uncertain, which means we know less precisely where the particles are. Even though in our head we somehow think that if atom is at zero temperature, it has, I don't know, some wave uncertainty, but if we have move it to high temperature state, suddenly it becomes well localized. So quantum mechanics kind of merges statistical mechanics, classical mechanics, wave mechanics, particle mechanics into a single framework. And statistical mechanics is part of quantum mechanics. And there were very recent, recent developments, I'm talking about 90s, so it's like already almost 30 years. And even I would say 70s when first steps were made, that in a way chaos is built in quantum mechanics, in the sense that if we study complicated systems, these sp orbitals, they actually become sort of like an orbitals of a random matrix. It's very unintuitive, very hard to imagine. Now going back to your question. So it's a statement I also saw in the school very often, that if we know positions exactly, we can predict and so on. And this statement is in a way, mathematically it's correct, there is no contradiction, but physically it's not correct. And for example, there are many, many reasons, but let me give you one reason, exactly quantum mechanics. Classically, if you want to basically have a well-defined trajectory of a particle, you need to have well-defined initial conditions, right? So it means that you should be, if you want to predict experiment, you should be able to place your particle at a point with fixed x and fixed p, right? P is momentum or velocity. So, but quantum mechanics is impossible. And quantum mechanics gives you the smallest possible uncertainty you can have. Classically, you'll always give something larger. For example, I also mentioned to students, the table we see is classical because its fluctuations are much bigger than those set by quantum mechanics, even though they are small on the visible scale. But then because of chaos, these initial uncertainties, they exponentially blow up. So it means that quantum mechanics, even if our dynamics is completely classical, it gives us limitations, how long we can sort of predict this three-body problem. And turns out these limitations are fairly small. There is a calculation which I didn't check myself. It's in review of Wojciech Zurek around, I forgot the year, the Reviews of Modern Physics. And he points that if you take Jupiter and its satellites, then just quantum uncertainty, meaning that you put coordinates and momenta of planets to an unprecedented uncertainty, like less than any possible measurement can give you, it's enough to basically make positions of planets completely unpredictable after 1 year. And 1 year is nothing on this big scale. So in this sense, the statement that we can predict everything in quantum mechanics, it's highly misleading in classical mechanics. It's highly misleading. So quantum mechanics, one has to understand, there are two things. First of all, we don't have probabilistic trajectories, but deterministic, trajectories, as you said. But also we have uncertainty. We cannot have precise position and momentum. And actually both effects are important.
So now, if you could describe to the audience, because I think obviously that's an important part of this podcast. What is the importance of this project? Like, what kinds of things could you imagine as, you already mentioned it's been an ongoing project for a while, so I imagine you even have some nice results already. But what kinds of things, what kind of uses could this research have in the future? What
Yeah, so maybe I'll say a few words about like just fundamental research, and then I'll try to talk about my work in this prospect. Yeah, I'm not really implying that I want to compare myself to big discoverers, but what I want to say is that lots of big discoveries, they came from trying to understand some questions. Perhaps the most famous is like Maxwell and Hertz. Like Maxwell in 1860s formulated some crazy theory that electromagnetic waves can travel in empty space. And moreover, they can travel with the speed of light. It just made no sense to many people how something can move in an empty space. It's empty, right? And then Hertz thought that, well, while it's crazy, it's good to test. And he made his experiment, right? And he didn't think about radio. He didn't think about applications. They were just trying to solve curiosity question. And then that's how basically all our electronics appeared, like radios and then, of course, TVs and everything. So, and this is just, I would say, a good example of how initial curiosity resulted in benefits which you cannot even measure in money. I don't know, trillions of dollars, like if you think about the effect of electromagnetic radiation. Right. So in this sense, generally fundamental research is kind of trying to answer some puzzles. But then, of course, in many cases, this doesn't lead anywhere. By anywhere, I mean to applications. And sometimes, when you are trying to answer puzzles, sometimes you find a negative answer. So you have an idea, you test it, it doesn't work. But when it works, there is usually like a huge benefit. So it's like imagining that we have a jetpot, which is like huge, which is much, much bigger than investment. But the point, you cannot keep it for yourself, right? Because this fundamental research, if it's there, it's published, anyone can use it. And this is sort of how it works. Having said that, we I believe that there can be some applications to my work, even though I'm not working actively on practical applications myself. So, like, just to mention most recent work we posted with my colleague Anusha Chandran, and also Dan Arovas, professor from UCSD, and the main person, of course, is a student, Bernardo Barrera, who did most of the work. We were thinking about essentially how you can generalize the idea of so-called pseudo forces like centrifugal force, or which you feel like, if you rotate very quickly, there is a force which pushes you. How we can extend it to quantum systems, which don't necessarily rotate. And technically, this is basically how we go beyond Born-Oppenheimer approximation. And this is one of the most powerful methods people use in chemistry, solid state physics, and so on. So, and interestingly, we found that the same object which defines chaos, it's generate of just element, it just defines chaos, let me put it this way. So the same term really defines all these extra forces. Now, whether it can be used, I hope yes, because we have sort of systematic way of going beyond this equilibrium calculations. But Born-Oppenheimer basically assumes that fast particles, they follow instantaneous equilibrium of slow degrees of freedom. And that's the only way you can hope to describe the systems. Like, for example, positions of atoms are slow and electrons are fast. But the example we mentioned, if you take a bucket with water and start rotating it, within this Born-Oppenheimer approximation, water will be always spilled down if it's upside down. But we know it's not the case because there are these extra forces. And then I think we found a framework how to generalize these ideas to quantum systems and more general notions. And I hope there will be applications, but it's hard to predict now. Then in my group, we also work in what's known as shortcuts to adiabaticity. It's basically how you generate fast dynamics, which keeps the system close to the desired state. A simple example, which you also mentioned in a paper, is a waiter who wants to bring bucket of water or glass of water through the room. So if the waiter runs very quickly, then water splashes. And that's exactly non-adiabatic effects. That's exactly this chaos I'm talking about, because once it splashes, you cannot control it, right? So the waiter, of course, can go very slowly. And this is what's known as a adiabatic process. And computations work in a similar way. If you do quantum computation very slowly, you're under control, everything is fine. But it takes a long time. But then the waiter can find a way around. And while, say, he runs, he tilts the glass a bit. And this is precisely a way to introduce some extra forces which suppress chaos. And again, we are thinking about how you can do it for more complicated, not necessarily more complicated, but more general setups, right? So you do quick computation or quick energy transfer or this or that. And this is, again, this is in sort of the direction of how you fight chaos, right? But as I said, in order to fight chaos, you have to understand it. You have to know well how it works.
So it's like if I think the classic example of controlling some kind of like chaotic system is you take a broom, right, and you stand the broom straight up and it doesn't in or controlling systems, I guess, in general, but you move the broom in order to keep it up. You make these little adjustments, and so this is sort of what you're doing in the quantum sense, right? You're making these
Yes,
little
yes.
controls to the Hamiltonian, in this case, the total energy or whatever. But
Yes, yes, yes. This is like example you're mentioning. It's known as Kapitsa pendulum. Yes, this is one of the example of how you control the system. So if you try to move the broom slowly, it will fall down in a predictable direction. But if you start moving it fast, indeed, you kind of stabilize it. And then you can think about not just controlling this upside down equilibrium, but also what kind of a series of pulses or how you should move yourself quickly, broom quickly, such that you go from down position to up position without falling down. So this is like kind of designing a protocol. So yes, yes, this is one of the examples how you can control chaos by fast motion. Uh, it's actually interesting, even though this is a simple example, but one of our findings, it was led by Peter Kleis, who is now in Dresden, that generally you can always, by shaking, achieve this sort of broom effect for any system. But of course, now, so for some systems, it's easier to do. For some, in a sense that there is a very simple shaking protocol, you just oscillate. And for some systems, you have to think about very complicated pulses. And one of the questions, how you design systems such that this broom effect is easiest to realize in the lab. But yes, it was perfect analogy.
yeah, thank you. So now uh, a question that I kind of want to ask everybody, just so that we can get the idea of this, because I'm obviously I also am in I you know we get funding. That's how my position is even paid for, right? So I think my question to you is the where do the funds go? What are you funding? Students? Are you buying computers? These kinds of things. Like what is it going to mostly?
Yeah, so I would say I'm a theorist, all right? And there is a big difference. So if you talk to experimentalists, of course, for them, equipment and operational costs, like liquid helium, whatever, it's a huge part of expenses. So for us, for theorists, yes, I use some of the funds to buy like computer clusters, to upgrade computer clusters, because a lot of work, especially when we deal with chaos, but generally a lot of work is supplemented by numerics. I have to say there are some groups which are really focused on numerics, like really do most sophisticated calculations, develop algorithms, so on. So my group is not doing that, but we still use simulations just to test our ideas or maybe get a feedback. So it's sort of like a way to do experiments, controlled experiments on systems. But this is like a small fraction of expenses. I cannot probably, it's probably, it's few percent, I don't know, maybe 5% and so on. Then also a small but very important part is travel. because it not just for me, but for students, postdocs, for everyone who is research. And sometimes travel means that we are hosting people. Because, yeah, we live in Zoom age, so some collaborations can be done over Zoom, but I would say personal interactions are still very important because you come, you share ideas on the Blackboard, you go to the same talk, then it resonates with what you worked on, then you catch the speaker and so on. And for students, it's also important to make connections, describe their work privately and so on. Again, it's not like huge part in terms of like a percentage, but it's very, very important. A lot of my work at least started from these random meetings. And sometimes even when you go to a conference which is not directly in your field, and then you see new people, that's how you get new ideas. And sometimes you share ideas they take. So, but the largest, of course, is funding of students. Usually NSF is sufficient to fund the student, graduate students, not enough for a postdoc, even though there are some bigger NSF grants, which are typically collaborative, like Malta University, they also have funds for funding postdocs. And of course, part is summer salary, usually 1 month, because faculty research in most universities, including BU, is not funded during the summer. So basically, during the summer, we don't get any salary, and then uh, usually from the grant, we are getting, say, 1 month from a grant, sometimes half a month, depends on the grant. So yeah, basically, this is how we spend most of funds. Then, of course, sometimes there are small publication charges and so on, but these are really tiny.
Yeah, I think one of the things that you mentioned, which I think is great, is yeah, I do think that travel is so important because I mean, if you meet face to face with somebody as a student, you know, that's how students find
Mhm.
jobs in a lot of cases,
Yep.
or things in the future. So I can definitely appreciate I can appreciate that as being of fundamental importance, and it's just not the same uh doing things over Zoom. Like I remember during COVID, the
Yeah.
going to meetings didn't feel the same, even though they tried their hardest to make it that way.
Yes, I would say my experience, actually, if I can say anything positive coming from COVID is development of the Zoom conversations and so on. But in my experience, they're great if you already have collaboration. I actually have many collaborations which started during conferences, but then we are working together, and then every like week or 2 weeks we meet and discuss, and then it works fine because you already decided what the project is, you're on the same page, you know the methods, and now you discuss details. But if you want to start something, it almost never works. So yes, I completely agree with you. With students, if you just want to find your peers, like basically immerse yourself into this physics circle, like share your work. It's very important to go to conferences. And I make sure that my students travel, I would say at least twice a year. And also, of course, we are lucky because in Boston, if you just try to go to every seminar, you will fill your day because you have, of course, I'm in Boston University, but Harvard, MIT, Northeastern, Boston College, also Providence, Brown is not very far. It's like on a commuter train, and other universities, UMass Boston, Amherst is not very far. So there is lots of opportunities to travel locally, and then either present your work or I mean, student work, or basically hear what other people are doing.
Now, you're a bit later in your career than me, of course, and so I'm curious, how many how many students do you figure you've trained? Maybe undergrad, graduate, combined. Probably, and I guess you probably have had some postdocs as well, right?
Yes, yes. Well, I didn't count, so it's probably. I mean, depends a little bit how you count. So if you take only students for whom I was like sort of the main supervised thesis advisor, basically, it's probably around 10, and I would say 3 or 4 undergraduates. I work more with graduate students because I personally feel that as an undergraduate experience, even if you want to become a theorist, it's good to have experimental training. And I always, that's what the case with me when I was undergraduate. I actually spent a lot of time in the lab, and I think it's very useful because physics is not about just solving equations. It's about relating some, I don't know, fundamental laws of nature to what we can observe. And math just is a tool which helps, like a language which helps us to relate. So then probably I had like 4 or 5 postdocs, maybe a bit more, 5 or 6. Uh, and then there were quite a few students who worked, who had joined projects who are not from my group or not even from Boston University, but with whom I still worked on joint project, wrote the papers, and probably there are also like at least 10 of them. So I think if you add numbers together, it will be probably between 30 and 40 people.
Yeah, that seems to be I mean, if you're at a research institution, at least, that seems to be definitely an important part of your job, right? Like, is you're training the next
Yes,
generation, and that's uh, one of the reasons for these funds is that you are training the next generation. That you need to be able to support them somehow. I know the universities have some money typically as well, but I feel like there's a lot of, from what I've seen, a lot of the NSF grants are, that's what it's paying for, is labor or equipment. Either labor or equipment is the main thing.
right, right. Yeah, I would say actually university funds are very limited. So there is some teaching fellowships, but it's sort of expected, at least in Boston University, that after 2 years, students are picked up by research groups, and more than 50%, I would say, of their funding comes from grants. But yes, I definitely view this as a maybe second and equally important part of research, fundamental research, is that we, I know, we teach students maybe how you can, how they can address complicated problems. I always mention, like, if students come to me and ask whether they can join research group, I always tell them that they have to understand that research is not like solving textbook problems, because when there is a problem in a textbook, it's known that there is a solution. When you're trying to solve a research problem, you even don't know where the solution exists. Exist in a sense that we can, with the methods we know, we can really make predictions, we can understand what's going on, right? Suppose we have some experiment which shows strange behavior, and we are trying to figure out what's going on. And of course, its solution in some sense exists because nature gave it to us. But within our formalism, within our capacity, it's not really clear we can single out this particular effect. Like out of atomic motions or molecular motion, can we figure out tornado, right? So, um, and then I also tell students that research is frustration, because very often they come and after reading some paper and they think, oh, it's beautiful, but one has to understand that this 4 pages of paper usually is a result of like, I know, 2 years of research. When you try this, it doesn't work. You try that, it fails, and you don't know whether your idea is wrong or code is wrong, or maybe if you describe an experiment, there is some artifact which is completely unrelated to the physics you are trying to understand, right? And then students, they really have to learn how you systematically analyze the problem, right? If you see the problem, you don't know where it comes from. Then you consider this limit, this limit, this limit. You try to see whether results make sense. Can you connect to something already known, and so on. And then you try many things, and finally you start getting a picture of what goes on, right? And after that, you can write a paper and so on. And I feel that this is a useful experience. At least many of my students and postdocs, they ended up in industry, some stayed in academia. I won't lie, I didn't ask them whether it was useful or not, but I hear directly and indirectly from other people that this was a very useful experience, because very often you have to, especially if you want to solve some problem, and it's difficult and you don't know the right approach, then these skills which they learned, they're extremely helpful. You know how to guess maybe a first model, through this model understand what's going on, then apply this intuition to your real system, and eventually end up with something practical and useful.
I think that's another reason why, in some ways, going to the conferences and stuff is important because you can actually hear the story. You don't see the story in the paper, right? But you can talk to the
Yes,
you can talk to whoever wrote it.
yes. Yes, yes, yes. And sometimes you learn from sort of from failures. So we usually, of course, if you get a great result, it's published in, say, great journal and so on. Everyone talks about that. But as a student, especially, sometimes you learn when you talk privately to people and they say they tried this, but they didn't work. But sometimes understanding why certain things didn't work actually allows you to come up with a different idea which might work. And this is also something you cannot, because when you read, I know, science, nature, whatever, you usually read success stories. But research is about, very often, it's kind of a painful road. It's sort of like you are trying to find a path in a new forest, and you have no idea where to go except that you have some general direction. You want to sort of build your quantum computer, reach the top of that mountain, but you don't really know what's the best way to do it. And of course, as you explore, you will often end up with bad decisions. But you learn from these bad decisions. You know, okay, oh, this direction is wet. I have like a swamp or something, so maybe I should go around, right? And someone else, maybe you, maybe someone else, will try this different direction, and finally, we will find something new.
I think that we've hit on a bunch of the topics already that a bunch of your explanations already, but I kind of wanted to give you a chance for the last part of this to because I thought you had a lot of good insights on this. Why you think fundamental research in general is important, going beyond your research.
Right. Yeah, I think it's one has to understand that this is fundamental research is a little bit like a prisoner's dilemma. So if you think about company, then very often it doesn't pay off to fund fundamental research, because in many cases, I would say 99% of the cases, nothing comes out of it. But in that 1%, uh, you will get some really breakthroughs, uh, uh, technological breakthroughs, like which will lead eventually to like, I know, a huge benefit for the society. I don't even want to measure them in mind, but like all good. I mentioned Maxwell and Hertz, but there are other examples like World Wide Web appeared at CERN, right, when basically physicists tried to find ways to communicate with each other. All semiconductor technology, like transistors and everything, which led to iPhones and so on, they emerged as attempts to understand how semiconductors work. And at that time, like in 40s, 50s, it was still fundamental science. More recent examples include quantum sensors, because quantum mechanics, with all this weirdness, it actually gives us best sensitivity. It's so sensitive uh, because particles, if you wish, behave like waves, and waves can interfere. And interference is very, very sensitive to phase. And this phase can pick up gravitational anomalies like cavities and so on. And it turns out that all these sensors, which are built more recently, they are now routinely used for GPS, for whatever. We just don't know. Very often, fundamental research is hidden in these technologies. So one has to understand that fundamental research typically appears in applications much later. We're talking about usually tens of years because the time, coming back to Maxwell, he developed his equations, his theory in 60s. Hertz tested them in 80s, and radio appeared, I won't lie, in the end of 19th century. So, I mean, now it might look like this is very close, but we are talking about tens of years. And with semiconductors, it's the same. First transistors appeared in 47 and personal computers in 90s. So we are again talking about 45 years. So why this is a prisoner's dilemma? Because usually if you hit a jackpot, you cannot keep it for yourself, right? So you invented radio waves. You cannot, maybe you can patent certain things, but of course at the end, all fundamental research is published. So once you have a discovery, some idea, everyone knows about that, right? So in this sense, a company can invest a lot and then everyone will share this jackpot. There were some successful stories like Bell Labs were funding dental research, but it didn't work out generally. So we need state support. But I would say for countries, big countries like United States, China, European Union, and we can keep going, there is a huge benefit, even smaller countries, of funding fundamental science. Because in terms of absolute money, it's a very small investment. And most likely, after some years, it will bring a lot of benefits. But then, why it's important to have in a given country? Well, because even if this jackpot spreads, it spreads among former students who know about this, who heard about this from the beginning, who can really understand these ideas very quickly and implement them in technology. So in this sense, if you only invest in applied science, I personally believe that after some time, after this 20, 30 years when new ideas will emerge, you as a country lose. And one has to say that I'm kind of repeating this point that if we just look into investment into fundamental science, I'm not talking about applications, engineering, and so on, just fundamental science, it's tiny. I mean, by the scale of other investments. And if we can accept that once we are trying to understand sort of new things, then they won't pay off quickly, and many of them will not pay off at all. But those which will pay off will bring huge benefits. Then I think it's more or less clear that we have to fund it. And I'm originally from Russia. There are many issues with this country now, but if we just think about science, it was, as we all know, science was at top level, like maybe after World War II, and mostly, of course, like this science related to the military was funded, and there, like Russia was doing pretty well, but it was also doing well in the level of physics, like lasers. Nobel Prize for lasers were given to Russian scientists, and there were many sort of big breakthroughs in science which are coming from there. But then after collapse of Soviet Union, science was not funded, and now um, it's very hard for them. They had many efforts of basically building high-tech industry. There were many government programs, and they didn't lead anywhere because they're just not in. There is no critical mass of former students, postdocs who are engaged in this scientific inquiry. So I think it's super important. And conversely, I'm not really expert, but I see that China is doing better and better because they're attracting more and more young people who are getting education in China, abroad, in US, in Europe. and they're attracting them back. And this also makes them extremely competitive, because these are people who know how to do research, and then they can innovate.
Well, thank you very much. I greatly appreciate you coming on and chatting with me about this. And I don't want to take up any more of your time, so thank you very much, and I hope to see you again soon.
Okay, thank you. It was a pleasure.